Okay, I clocked in at about 7.5 minutes. I'll try to do this one in less time than that even. We're throwing a dart at this target, and we want to know what the probabilities that we hit the bullseye. It's just the, this is a problem about the geometric probability of this situation. So it's just find this area. This area then, if it's a side of 6 centimeters, it's 6 on each side, that's just going to be a 36 square units of area. If it's centimeters, then that's what it would be. The entire circle has a diameter. The circle has a diameter all the way across of 10, so the radius there, r equals 5. R squared times pi is our area, so that's 25, 5 squared times pi. This is very close to 46% when we work that out, okay? Two friends are planning to meet online and chat, so this is one of those geometric probability questions as well. This would certainly be something you could do by coming up with a simulation. Notice I give you a major hint there that it's 100 minutes. Make sure you do the subtraction with minutes. Sometimes it's easy to make a mistake because there are 60 minutes in an hour, not 100. But in this case, 8:30 to 10:10 is 100 minutes. So there's 100 minutes there and there's 0. If you were to do this with a simulation, you would just get two random numbers from 1 to 100. You'd press it twice, and you'd see if they are within 30 minutes. And if they are, you'd mark it with a smiley face or whatever, and if not, you wouldn't. And then you keep a tally. If you did about 20 or 30 trials, you get very close to the correct answer. So on the test, if you get stuck doing this, you could always try it that way. In this case, though, we're going to do it using theoretical math. So we know that this is our sample space of possible places where these two friends could both log on. We're looking for the fact that they will connect, and that's going to be the zone that goes like this, where this point right here represents 30, 0. So if the first person down here, friend A, talked immediately, they could be online for up to 30 minutes, and then, if person B here logged on first, then person A would have to log on within 30 minutes to connect even for an instant with them. So this point right here then is going to be 0, 30, and out here now, this distance is going to be 30, so this is going to be at the point 100, 70. I don't know if that shows up, but it's going over to 100 and then up to 70. So this is where they do meet. Their numbers are close to being together, approximately equal. This is the line where x and y are equal, and they log on exactly at the same time and can be online together for 30 minutes. But this is where they do not connect, okay? And so I need, whoops, that's my upside down smile. We need to figure out what is the area of this, because what's the probability that they will connect will be this inside area. It's easiest to think outside and then do the subtraction. So I'm going to take this triangle here and add it to this triangle here, and I end up with a square that is 70 by 70. So 70 squared, then over, and this is 100 squared. Well, that's going to be 4,900 over 10,000. That's 49%. When I take that away from 100%, I'm going to get this probability right here of being 51%. Okay? So that's the answer for that one. Very close to 50-50. Okay, what are independent and dependent events? Independent events are events that do not affect each other. I can toss a coin, I can pick it up, I can toss it again, the probability is the same. That's an example of that. Dependent events are events where when you've done one thing, it somehow affects the probability of something happening again. The simplest example is where we're choosing socks out of a sock drawer. Okay, you wake up early in the morning and it's still dark out, and you've got white socks and black socks, and you're going to choose your socks for the week or something. If you choose a couple of pairs of black socks, or even one pair of black socks, the fact that you're reaching in again to choose a second or third pair, the probability has changed because you've removed one of them from the drawer. And that is an example of dependent events, and you just want to be aware of the situations that will produce dependent events. Okay? Number 9, a game is played with a 6-sided die. That's actually a typo. I meant for it to be a 4-sided die, but I'll just go with it because I bet you've done the problem that way. If you roll a 1, you win 1 factorial, which is just $1. If you roll a 4, you win 4 factorial. Now, I apologize for abbreviating this. I talked about it, I think, in class, but you're supposed to fill in 2, 3, 4, 5, and 6. And so 1 factorial wins you 1, 2, rolling a 2, 2 factorial is 2, 3, rolling a 3 wins you 3 factorial, that's 6, and 4 gives you 24, as I showed there. 24, I'm already thinking about 5. 5 factorial is 120, and 6 factorial is 720. So these are your possible earning amounts. You multiply each one of those by the probability that they happen, and each one of those probabilities is 1/6. When you multiply each of these by 1/6, here you get 120, here you get 20, here you get 4, here you get 1, that's 1/3, and that's 1/6. And you add all that up and you get, let's see, 145 and 5/6. Okay? That's your expected value. That's pretty good. $145 plus. I definitely would think that you'd need to charge, like, if you're a casino, you're going to charge $150, and then on average you'll make $5 per game. Okay? You lose, of course, if somebody wins 720, but most of the time you're going to win. Okay, what's the probability that a family of 7 will have 3 or more right-handers? If you're talking about the probability of 3 or more right-handers, think about the probability of 3, the probability of 4, the probability of 5 right-handers, 6, and all 7 right-handers. You'd have to find those 5 probabilities and add them all up. It's actually a little bit easier to find the reverse of that. Find the probability of only 2 right-handers or less, which is 1 or no right-handers. So if I find the probability of 2 right-handers and the probability of 1 right-hander exactly and the probability of no right-handers, all left-handers, and I work out those probabilities, I can add them up and then subtract that from 100. Now it turns out that these probabilities are very low. I wanted to see how you handle these crazy low numbers. Don't get too worried about it. The probability of finding exactly two right-handers is going to be 7c2 times 0.89 squared, then times 0.11 to the 5th power, because there are 5 that'll be lefties, 2 that'll be righties, and then that's the number of ways that they can be mixed all together. When you do the math, you're going to get 0.000, 3 zeros, 26 as your percentage, okay? Sorry, as your raw probability. You can move the 0 2 places, and it's going to be a little less than 3/100%. These other ones are even smaller, and when you add them all up, you get almost exactly 3/100%. So it's extremely unlikely. When you subtract from 100, you get 99.97%. Okay? Now, on the test, I'm likely to give you a little bit more reasonable numbers, but it's the theory that I wanted to see, and on your quizzes, it looked like many of you did that correctly. Okay? We're all done. I'll post the answer sheet online.